In this work, we propose proactive model adaptation against concept drift for online time series forecasting. Due to the dynamic nature of the environment, latent concepts, for example social interest, stock market sentiment, that influence time series often change over time. This phenomenon is known as concept drift. Future test data may not follow a similar data distribution as the historical training data, causing degradation in forecasting performance. Online learning is a common solution. The key consideration is to continually transform the newly observed time series into a set of training samples and adjust model parameters by minimizing the forecast errors. Existing methods focus on how to effectively adapt to recent data by utilizing forecasting feedback, for example errors or gradients on the new training samples. However, these methods overlook the fact that the ground truth of each prediction is not available immediately but is delayed after the forecast horizon. For example, at online time equals 5, we use values from V1 to V5 to forecast future values V6, V7, V8, while the ground truth is known until equals 8 and the feedback of forecasting performance arrives with 3-step delay. As a result, a temporal gap always exists between new training samples D and the test sample 10, where concept drift may occur. This suggests that addressing concept drift by fitting the forecast model to the recent training samples may be insufficient, since concept drift may also occur over the step temporal gap between the recent training samples and the current test sample. To address these issues, we propose a novel framework that proactively adapts the model to each test sample. We conduct extensive experiments on real-world time series datasets. Results demonstrate that our method remarkably reduces the average forecast error of different forecast models by a large margin of 22%. Moreover, our method outperforms existing online model adaptation methods by an average of 11%. Also, we compare the GPU memory occupation and inference latency of different model adaptation methods on the traffic dataset. We achieve the lowest online latency and low GPU memory occupation, showing high efficiency. For more details, please refer to our paper. Thank you.